Well, good morning, everybody. Today we're going to talk about the work done by conservative and non-conservative forces, and we'll define what a conservative force is, and therefore what a non-conservative force is. There's several non-conservative forces, and then we'll deal with some problems involving energy. So, first of all, what is a conservative force? Well, we have two of them so far. We have two conservative forces, and they are gravity, the force of gravity, and springs. Now, what do these two forces have in common? Well, first of all, we have equations that describe potential energy for these two things. Like the potential energy due to gravity, U sub G, is equal to mgy, and the potential energy due to springs, the elastic potential energy, that's what that E stands for right there, is 1/2 the spring constant times my position squared. Now, recall that we have this stuff we call mechanical energy, and it's really mechanical energy by definition, and we give it a variable name of E. Mechanical energy is defined to be the kinetic energy an object has plus the potential energy it has, and this U here can represent either one of these. Now, if a force is a conservative force, there are two things that are true. Well, let's say an object is located right here in space. We'll call this point A, and here's point B up here. A conservative force is when a conservative force does work, when you're moving from A to B, it doesn't matter what path you take. I can go from here, I can take this path, I can go straight from A to B. I can do that, and I can figure out how much work was done. I mean, here's my displacement, and maybe there's some force, and the force can be, it doesn't have to be along the path, obviously, right? I mean, this could be like a track that restrains the object to move along this path, even though there's a force acting on it that's in a different direction. If we, figure out how much work was done by that force, okay, we'll get a certain amount of work, right? Well, what if the constrained path looked like this? Like that. What if you had to follow this path right here? Well, if the force that's doing work is a conservative force, then it wouldn't matter whether you went from here to here or you took some random path. The work done is independent of the path. Now think about gravity for a second. If I was to pick something up, if I was to pick up a textbook or something, and I was to pick it up and I was to go woo, like this, and maybe this is like a shelf over here. Here's the floor. Maybe this is the floor, and here's some maybe this is a tabletop or something. I could pick it up and just move it straight up and move the book right here. Or I can go woo. I don't know. I guess I drove the book into the floor, and then I lifted it up and I spun it around. Maybe I was dancing with a physics book, and then I put it right here. If I look at the work that was done by gravity, not by me, but by gravity, it wouldn't matter, because the work done would just add up. When you go through all of this, it would just be mgy, right? It would just, all the work done by gravity only depends on the height that I lift it up. So this horizontal motion doesn't matter, and only the vertical motion matters. And if I have a spring, it's the same kind of a deal. Let's say here I have a rubber band, which is an elastic material, and let's suppose I'm going to go from A to B. Okay, I could measure the force of the rubber band and stretch it out, figure out how much work was done by the rubber band. Well, here's what we mean by a conservative force, that if I go like this, look at this path, I'm just going all over the place. I can even go off to the side. If I go from A to B, the spring force, or the elastic force of the rubber band, did the same amount of work as if I just do this. Now that's because of, this line integral right here. I mean, let's think about gravity for a second. Right here, when I go from here to here, if this is my little dr right here, then gravity did negative work, right? Because the force of gravity is down, but this is up. And when I go down here, from here to here, it did positive work. And so the negative work here and the positive work here tend to cancel each other out. And that's another characteristic of, here's another characteristic of conservative forces, is if I end up where I started, that is, if my path looks like this, if I start at point A and I end at point A, and if the work done by a conservative force will be equal to 0. And we'll call it W sub C. W sub C. And W sub C up here is path independent. Okay? So the work done by a conservative force, so this would be a conservative force right here, is path independent. And here we say the work done by a conservative force equals 0 if you end up where you started. Now this kind of makes sense. Let's take that textbook and think about gravity here for a second. And if I lift it up and then bring it back down, well, on the way up, gravity's doing negative work, and on the way down, it's doing positive work. And if you add all that work up together, you get nothing. Same thing is true with a spring or an elastic material. If I start here and go follow this path and end up where I started, okay, here the spring is doing negative work, and then on the way back it's doing positive work. Now remember, this is the work done by the spring or the rubber band, not the work done by my hand. Don't get confused. Here the displacement is up, it's positive, but the force applied by the spring is negative. Okay, and if I add it up, and it doesn't matter what path I take, from A back to A, the work done by the rubber band here is going to be 0. So the elastic force is a conservative force. And what we mean by a conservative force is this. It's path independent, and if you end up where you started, the work done is 0. These two things kind of say the same thing. But that's what makes a conservative force. Now, if you have a non-conservative force, well, the work done by a non-conservative force, it will depend on the work done by the force does depend on the path. Okay, and there are there's a really easy example of those. So non-conservative forces. Well, the two I'm going to illustrate here are applied forces. applied forces and friction. Now, let's look down on a tabletop here. Actually, I could just do it right in front of you here with the document camera. Here, I have, I could do it on the paper. Let me get a fresh sheet of paper. Let's make this point A, and up here is point B. Now, if I'm going to move the eraser from point A to point B, there's two things going on here as I move from A to B. Well, I did work on the eraser because I had an applied force, and I pushed it all the way over here, and I can measure this displacement, measure this force, and that's how much work I did. I did positive work to the eraser as I moved it. Now, this thing didn't gain any kinetic energy, and it didn't gain any potential energy. No mechanical energy was not changed here. Why is that? Because there was also friction, right? And the friction was opposing my motion. And so the energy that I was putting into the eraser, well, the friction just turned that energy transferred that energy into the internal energy of the eraser material and the paper. It just warmed up the environment a little tiny bit. So there we go. All right. Now, but this is the amount of work done by my applied force going from A to B, and by the force of friction, is path independent. Because if I go like this, and then I turn it and go like this, right? So my path was much longer, but the force was the same. So I did a certain amount of work here and a certain amount of work here. Well, that's much more work, a little bit more work, than going straight from A to B. In fact, if I zigzag across here and make the path really long, I had to do a lot more work than just going from A to B. Now, the reason for that is, I mean, if the eraser's right here, and I draw a little free body diagram of it, here's the force of friction, and here's my if I'm pushing like this, here's my applied force. Well, when I wanted to go turn this corner, my eraser's like this now. Now my applied force is pushing like this, and my force of friction, is in that direction. Well, the force is turning along with the path, and so I think you can easily see that the longer I make the path, because I have to turn the force to make it go in that path, you know, back and forth, that the amount of work done does depend on the path. And also, what if I go like that from A to B, and then from B back to A? Well, here I ended up where I started, but my applied force did not do zero work, and the force of friction did not do zero work. So the applied force and the force of friction, by my definition of conservative force, you know, the work done was not zero. And so therefore, friction and applied forces are what we call non-conservative forces. Okay, well, you know, that probably hasn't changed your life for the better yet, so let's move on. Why is this important? Well, here's an idea. If a conservative force, like the gravity or a spring, if it's doing work, and here's a real easy example. Here's the ground. Here's my little eraser, okay? I'm going to hold it right here, and I'm going to let it fall to the ground. All right? Now, I think it's easy to see that, look, here's the force of gravity, And here's my y initial. Here's y final. Maybe we'll just look at it just before it hits the ground. So here's delta y. Well, let's take a look at the work done by gravity here. It's just going to be the force times the displacement. This is the work done by my conservative force is equal to mg delta y. But I think that it's very easy for you to notice something here, that when I go from here to here, I'm going to lose gravitational potential energy. Okay, now this is a big deal. When a conservative force does positive work, I'm going to lose gravitational potential energy. And so what I can do is say this: work done by the conservative force results in a loss. In other words, delta U is going to be negative. Okay, when when this quantity right here is going to be a negative quantity, we lose gravitational potential energy. Now, if this is the only force acting, where does that energy go? Well, the work done by that conservative force, now the conservative force is the net force, and that will be equal to an increase in kinetic energy. Okay? So, if you have a conservative force, and in this case we're talking about springs or gravity, the kinetic energy will be increased, but at the expense of potential energy. And now this works for springs just as well as for gravity, so I'm just going to leave it here. And so what we can say is that the work done, now let's add this to the other side, the work done by a conservative force, well, will be equal to, no, that's not right. Hold on. Well, we have delta K plus delta U equals 0 now if I put this on the other side. And what this means is that the work done by a conservative force, let me zoom in a little bit. The work done by a conservative force does not change the mechanical energy of a system. So, if a conservative force is doing work, it doesn't change the mechanical energy of the system, because it's, really what's happening is you're just going to pour the energy into kinetic energy, or you're going to take the kinetic energy away. Okay. Now this brings us to non-conservative forces, and it also leads us to what I think is probably one of the most useful equations that you're going to get this year. It's right up there with F equals ma, and ironically it's not in your textbook, so really pay attention right now. Okay, here's that equation. if you have a non-conservative force, what a non-conservative force does, it is the work done by a non-conservative force, that's going to be equal to the change in mechanical energy of your system. For example, an applied force. Now, here's my eraser, and if I were to put an applied force to it, this thing is going to increase its kinetic energy. Or if I have an applied force here, the normal force between my hand and the eraser is an applied force, and I were to lift this thing up, okay, I'm increasing the mechanical energy of the system, right? I'm giving it gravitational potential. In this case, if there was no friction to slow it down, if I applied a constant force like this, it would go faster and faster and faster. I'm at my non-conservative force, my applied force is giving it kinetic energy. Or here I have a non-conservative force, my hand pushing on it, lifting it up. I just gave it, I changed the mechanical energy. I gave it gravitational potential energy. Okay? So what you can do is you can say this. You can start every energy problem with this right here. This is a beautiful equation. The work done by non-conservative forces will be equal to the change in mechanical energy of your system. And what's nice about this equation is that it works even for problems where there are no non-conservative forces. Let's say that there are no applied forces, there's no friction in your problem, and you say, oh, there is no work. So you put 0 equals the change in mechanical energy. In other words, if there are no non-conservative forces acting, then then you won't have any change in mechanical energy. Delta E will be equal to 0. And you can use that. Of course, that leads to, well, this is E final minus E initial, and that just leads to the conservation of mechanical energy equation, where the final mechanical energy equals the initial mechanical energy. But this equation works in every problem. This is always true. If you have non-conservative forces acting in your problem, then they will change the mechanical energy in your system. So if you're working an energy problem, you can always start here. You can start with that. And so, I think we'll leave it there. There's a bunch of example problems for you to do, so why don't you get on those? All right, bye-bye.